so I defined this new matrix thing called an inverse. You may be asking yourself, so what? Well, the main use of a matrix inverse is to compute solutions to linear systems. It all comes back to that matrix vector equation that we know and love. So here's a theorem to justify that. If A is an invertible n by n matrix, n by n matrix, then for every B in Rn, the equation AX equals B has the unique solution X is equal to A inverse times B. So if I have a matrix, a system of equations where the matrix is an n by n invertible matrix, I know that that system has a unique solution, and the unique solution can be found by taking the inverse of A and multiplying it by my given vector B. All right, we got to justify this. This is an example of an existence and a uniqueness proof, right? Because there exists a solution. I told you what it was, and I claim that it's unique. So let's first talk about existence. All right, I'm going to let B be a vector in Rn that's given to me. And I'm going to construct X by my formula, A inverse times the vector B. Then what I can do is I get A times the vector X is going to be A times the vector X, which is A inverse times B. Reassociate this. A times A inverse by definition is the identity. The identity matrix times the vector B is just going to give me the vector B. Okay. So what this line of computation shows is that the proposed vector X is in fact a solution to the equation. Okay. Next, I need to talk about uniqueness. So we already did a uniqueness proof earlier, so we're going to do that again. Except this time, what I'm going to do is I'm going to say, I'm going to pretend I'm given a solution of this equation, and I have to show that that equation has the same form. Okay, it's an equivalent idea. So suppose the vector u is a solution to A times X is equal to B. Okay, so my goal is to show that u is also equal to A inverse B. Okay, so that means that A times the vector u is equal to the vector B. What I'm going to do is I'm going to multiply this equation, multiply on the left by the matrix A inverse. Okay. So we have to specify when we're talking about computations involving matrices and multiplication, if I'm multiplying on the left-hand side or the right-hand side. Okay. If I'm multiplying on the right-hand side, A inverse times B doesn't make sense because the dimensions don't line up correctly. All right. So in order for this to make sense in terms of the matrix vector computation, it has to be on the left. So that turns us into A inverse times the vector AU is equal to A inverse times the vector B. Well, on the left-hand side, I can reassociate this. This is A inverse A times the vector U. Well, A inverse A is indeed just the identity. So I had the identity times U is equal to A inverse B. which means that U is equal to A inverse B. Okay? So this shows uniqueness in the sense that it doesn't matter what solution you give me, okay? That solution will also have that same form, okay? So that means that that form that I have, it must be the only one. Right? It's kind of like the wonderful thing about Tigger's is I'm the only one, right? Put her back to Winnie the Pooh. Wow. I know it's lunchtime. Y'all are starving for knowledge and food. Okay, does anyone have any questions on this proof here? On what's going on? Yes, Courtney. So I'm multiplying both sides of the equation by an A inverse on the left, right? So I'm multiplying on the left-hand side of each side of the equation. So I'm multiplying this equation by the matrix A inverse to both sides. That's to maintain equality. But then since I'm talking about multiplying by a matrix, I have to specify, am I multiplying it here or am I multiplying it over here on the other side? So that's why we say multiply on the left by A inverse. So it's the same basic principle that we have in algebra of multiply both sides by the same thing, but now I have to give the special instruction of what order am I multiplying.